So we're going to take a big step backwards and go back to the beginning where we started to talk about datification. We're going to talk about datifying stuff and quantifying stuff. And for me, the two are very, very similar. You can't really datify anything without counting it and recording it in some way. So the essential step of datification is quantifying observed phenomena, right? So if we want to know how many suicides there are, we count how many people have died, right? It is basically counting things. Counting things by itself is rarely very useful, and so often we will count them in a way that we can compare them. And so that is batching them into categories. How many people died, for example, in the United States versus in Mexico over a period of time. So each of those are constraints we put on those counts. So now we have not just a single count, but a count in two categories. Or as I said, over time, you could say how many people died in 2020 versus 2022, right? So we have these little baskets that we can put our counts into. At a very basic level, that is most of what we do. We can do a little step up to this and say that the way we record those data are not just a matter of yes or no, which you could say about deaths, perhaps, that someone is either mostly dead or mostly alive. So that might be a binary kind of a metric. But really we build up from that to start to talk about, can we represent things as being one of a multiple set of possible categories? This is what is usually referred to as categorical data or nominal data, nominal being sections that are named, right? We can move from that to something like ordinal data, that is first, second, and third rankings. One, you have different categories, but one is above another. And then the next step is usually interval, that is steps, although I very rarely use these. And then we get to the king of all measurements, which is continuous variables, and usually what is called ratio variables. And these are marked by being on a continuum, thus continuous, and usually with a set zero mark that is a standardized zero. You can actually do comparative as well, so that you're doing a ratio between two possibilities. This is how we have things in meters. 0 meters is the same as 0 feet, so it has a fixed zero. But what is 1 meter? It's how closely you are measuring against a particular, originally a rod in Paris, but eventually a subsection of the length of light or whatever. So it's a comparison with a known standard. When we record these things, it is with the intention of interpreting them. And so if counting is the core quantitative form of representing observations, narrative is the core qualitative form of observing things. So when you ask someone for an eyewitness account, they're telling a story, a narrative about what they saw. Now, very often, in the scientific enterprise, it is a combination of these two things. I cannot imagine collecting data that then is not informed by a story about what we're trying to collect, and then informs a new story. That interpretive process of using those quantifications, of using those counts, is always a storytelling process. Likewise, although there are certainly narrative processes that do not rely on any quantification of data, that is growing, I think, increasingly rare. That there is value, people that do more interpretive work recognize that there is value in the count to their narrative process. So we've talked a little bit about the use of, for example, thematic tagging, which is frankly a quantified process, right? You are, in that case, using categorical data to assign particular names to certain events within the data itself, whether that's let's say a textual data, an interview that you're then coding afterwards to make more sense of. That process is a quantification of the data. Certainly when we talk about something like doing textual analysis that relies on something like machine learning, that's a massive quantification of the data. But the story we tell about that quantification is still important. How we decide to encode this language into counts has a really important influence on what we get out of the story we get out of the back end. So let's talk a little bit more about what that means on the analytical side. What do we do with these numbers once we have them back? So I've given an example. How many people? Let's move it out of suicide and just died. How many people died in Mexico versus how many people died in America between a certain number of years? That is a very sort of an essential process, right? We know that. Let's assume that we have a data collection process that's fairly accurate. Who knows, that gets us a full count of how many people died in each country. It's pretty straightforward at that point to say, where did more people die? In Mexico or in the United States? This is something that is, as an analytical process, no matter how much statistical training you've had, you probably can accomplish this without trouble. You might actually be able to do more than that and say, well, that's not a very useful set of variables to compare. Hopefully you've jumped to that pretty quickly, that you want per capita death rates if you want to have anything useful out of this particular metric. It doesn't really matter how many in total died, but if you have a higher death rate in one place or another, that might help to inform some questions you're trying to answer, right? We could give some examples around COVID, for example, about what geographic categories had higher rates of infection and death, what socioeconomic groups did, what sets of practices might have influenced whether someone died of COVID or did not. Not individually, but as a group, what the chances were that you died or did not die were closely related to some behavioral choices, for example. So by batching these and then engaging in comparison, you can come up with some indication of whether something is happening or not happening. Even at that point, you can run into some slight problems in the logic, but most of that is about the story I've been telling about that, right? We'll get there in a second. We'll talk in a minute about some of the basic statistical abilities you need to have in order to kind of engage in this, but the next kind of step you might want to be looking at is whether you can infer something as a standard or as a norm based on the observations of just one thing. For example, I can only really have observed things that happened in the last 5 minutes, the last 5 years, and the last 5,000 years to varying degrees of accuracy. I cannot observe what's going to happen in the next 5 minutes, the next 5 years, or the next 5,000 years. I just can't. If someone knows how to do that, awesome, but that is not within my skill set. So, at a very basic question, at a very basic level, when we are making observations about the world, we are hopefully able to make some kind of inference about whether this is a generalizable phenomenon. Now, we can just describe, right? At a very basic level, we can say, we know how many deaths there were, and I'm not saying anything beyond that. But often when we're doing this, we're trying to engage in something that allows us to do one of two things. If you've been through any kind of theory course in any of the social sciences, you've probably run into how you assess what is a good theory. And there are a number of things, parsimony and kind of the breadth of explanation. Different people have different schema for kind of ranking. This is, again, a category and ranking, a quantification of a theory, but different sort of rubrics for deciding whether a theory is good. But very broadly, there is a division between those who see the very best kinds of theory as explaining the world or predicting the world. Obviously, the ideal theory would both explain and predict the world. But if you have a good model and a theory that explains how things work within that model should help you to either explain why things have happened, ideally, or to predict what will happen. The prediction piece tends to be something that is valued in the natural sciences more. The explanation of it is sometimes not as heavily sort of valued among those, especially from the positivist bent. So, for example, to take something outside of the social sciences, can I predict whether a rock or a feather will drop to the earth faster, or neither, as the case may be, in a vacuum? So can I predict that? Yes, I can predict that. We had a set of now laws, natural laws, that give us, based on a set of many, many observations under many different conditions, that give us, within at least a bracket of, as long as we're not approaching light speed or getting very, very tiny, very, very fast or very, very tiny, I can predict with really good accuracy how long it will take for those to go from the top of my house to the ground, right? Can I explain to you how gravity works? No, I don't think anybody really can explain to you why it is that they do that. They can say, if we know this about them, how quickly they will fall, but we can't say why that is. We can't say what mechanism allows that to happen. We still don't know that. So it's an extraordinarily strong theory, the theory of gravity. I believe in it. I'll stand on that. But it is one that does not provide explanation. In the social sciences, we don't have a lot of those predictive ones. I will say there's some wiggling here. If you've read the Foundation series by Asimov, you know that there is this idea that perhaps if we had a really good set of measurements, we could predict with some degree of accuracy what groups will do, even if we could not predict what individuals will do. There are still many social scientists who believe that this is the case, that we cannot, for example, say with any certainty what an individual would do. We might be able to give a spectrum of probabilities that they might do one thing or another given a particular stimulus, but we can say with more certainty what social systems will do. I don't happen to fall into that camp. I think there are some severe limitations to the prediction of mass sort of social action. But there are those who say, okay, we should still strive for that kind of prediction. There was a pretty famous set of government-funded attempts at predicting social science. I mean, this goes back really for a very long time. In the United States, since the 1930s on, there's been a stream of attempts to be able to predict the outcome of large social events. And with big data, we've gotten closer and closer on this. There was an outgrowth of a program that was originally called TIA, Total Information Awareness, which freaked out a lot of people, not without reason. And so that name got zapped. It was a leaked PowerPoint that had the logo had, anyway, the logo I think freaked people out more than the actual content, but the content did too, which was if you had enough surveillance, you could predict the large scale social changes. And some of that funding recently was apparently pretty accurate at predicting social unrest. That is, would there be people out on the streets protesting? And they drew on a bunch of different data to try to determine this. And part of the reason it was reasonably accurate is that it brought in such a very large number of variables. It looked at things like the weather. It looked at things like the time of year. It looked at things like large-scale interpretation of news releases. It looked at, it drew in data from reservation systems to see who had made reservations at restaurants. So it took a bunch of this stuff in, often without telling a story in the front end, with this idea that if you had enough data coming in about traffic data, road traffic data, if you had enough of that, you would be able to predict whether there was going to be a protest or unrest. And it seemed to do that with some accuracy. So even though it's very difficult to kind of do that prediction, it's not impossible. And I think that we will see more and more ability to predict, especially high variable complex systems, including social systems. Again, never perfectly, but to the degree that it is useful. We're not going to get laws in the same way as we do in the social sciences, or rather in the natural sciences, where we can say all things being equal, we know what the acceleration due to gravity is. We're not going to get that same sort of set of natural laws for social systems, but we can probably get increasingly accurate predictive laws within certain brackets again. That explanatory piece is more intriguing and I think more interesting to a lot of social scientists. Something has happened. Can we explain why? And counting can be a really important part of that as well. All right. So at its root, we're looking at comparisons, and then that piece is we're looking at whether we can find relationships. We can do that by looking at the numbers alone, but usually it's a question of whether we have collected the right information, the right data, and recorded the right data to be able to make those comparisons. At a very basic level, we can look at whether things covary, that is, whether variables move together. This is correlational work. And especially as we increase the number of variables, we can find that lots and lots of things within a complex system covary. When I say covary, it means that, for example, when one variable increases, the other increases. When one variable decreases, the other decreases. This is famously the source of a number of spurious correlations. That is, you can find examples of things that seem to correlate because they seem to link together in their values over time. But this is simply because sometimes things accidentally fall together. So you have to think about the probability of that happening at random. And as you increase the number of things you're observing, you will find more and more of those correlations that occur simply at random. And so this question of the probability of a correlation being spurious or something that is confounding that measurement, that is, it may be both may be an outcome of a variable you haven't even looked at, you're not counting at all. Those increase exponentially as we get to this era of big data where there is an exponentially larger number of potential sources of that data. So thinking through that part, which is not really statistical and more methodological, becomes much more important as we get to bigger and bigger collections of different counts, of different variables. Part of that is because everything is connected. This gets us to not necessarily social network analysis, but this issue of complex systems and multiple relationships. Again, the causational piece is a piece of it. That is, how do these not necessarily cause one another, but how do they influence each other? But the problem is that everything influences everything all at once. So that is the knot that we have to kind of untangle, which is, if everything influences everything all at once, are there pieces that we can tease out of this that are useful to explain a particular phenomenon? Is something especially influential? If we know, for example, that under certain conditions people learn better, I can tell you that Dr. Pepper increases math scores. I know this from both anecdotal data, and there have been studies that show that if you give people a glass of Dr. Pepper before they go to a math class or before they take a math exam, that will improve their math score. that is a correlation. It is. I think we can do some causative work on that. I don't think that going to math, in my case, it probably did, but I don't think going to a math exam is going to cause you to drink more Dr. Pepper. But I think that we can kind of look at some timing there and at least infer that there's a causation. But the question is, does that matter? Because when everything is connected, the fact that Dr. Pepper improves your math capability doesn't really matter as much as some other things that might also improve your math ability. It doesn't matter because it doesn't matter if you everything else being equal, it might matter, but everything else being equal doesn't really matter in social systems. Like, we cannot tease it out in the same way. And also it drives diabetes. So like, you have to think about what the other potential outcomes are that you're not measuring. If you're solely focused on math scores, there's lots of things you could do that would increase math scores on exams. If you were solely focused on math scores on exams, there's something seriously wrong with you. So we have to think about both the vast number of potential inputs to a particular outcome and the fact that that also has huge outcomes within this complex system. All of this gets very, very complex very quickly. And so the story of how we select what things we're measuring and what outcomes we're taking from those measurements, and then how we pull that back out into an interpretive story, is kind of the pathway that is most important. Part of that, and not part of this class, but another class, is how we visualize that. Visualizing, especially quantitative data, is another form of storytelling. It is also intimately tied to this question of how we select data and how we model it. So the choices we make in telling that story visually are also really important. What we exclude, because making a model always means excluding things, is also very important. And especially when we're talking about very complicated data and then trying to depict it in two-dimensional spaces, it can be very, very easy to mislead when we do that. If you went through that very long lecture on social network analysis from Bernie Hogan, you saw about an hour in where he talked a little bit about how the different ways in which people were measuring an outcome made it almost impossible to compare them, and also that this is not necessarily about visualization; it's about machine learning, but they are a similar issue. That when you reduce the dimensionality of what you're visualizing, when you take something that is, I'm going to take one big step back. I'm assuming in this process that you guys understand what kind of multidimensional scaling is and what I mean by reducing dimensions. And in case that I've made a mistake on that, because I think a lot of people haven't really thought about this, I'll take a slight detour to talk about that. When you have data that is often network data, you have information about how people, for example, relate. This gets to flatland in some ways. So I have a friend named George, and I like George a lot. I have a friend named Sally. I like Sally a lot. This goes back to relational dynamics in psychology and also in social sciences and also in political science. You get this question a lot. So because I like George and George likes me, and because I like Sally and Sally likes me, let's just assume that this is an undirected graph and the love flows equally among us all. Do George and Sally now get along? Now, leaving aside the theoretical questions about that, let's just assume that they don't. This messes things up. But let's just assume that they don't. If they do, we can draw a graph of us as a triangle and it works out fine, because there are two dimensions in that, how much we all like each other. The minute that one of us does not fit into that equilateral triangle, the minute that, for example, Sally and George are on the outs, we now have three dimensions we have to measure. Not sure how I can say this, but if you think about the chart that gives us, it's going to be a 3x3 chart, right? So that can be two-dimensional, but really it's in this case, more likely three-dimensional. That is, the weights between all three of us are going to be in 3 dimensions, literally 3x3, right? If we charted this in a 3x3 chart rather than trying to draw it, we would have 3 on each side, right? And now, admittedly, down the middle of it, assuming we like ourselves, which often I do, assuming we like ourselves, that's a line down the middle, but then we have at least half that triangle in this case, because it's an undirected graph, or if it's a directed graph where I can like Sally, but she might not like me as much, we still have a 3x3. So that's a 3-dimensional graph. And we can chart that on, if I had 3D goggles, but if we do it on the page, it is literally, we are stuck at those 2 dimensions. We can fake it, right? We can do a projection where we can kind of see the axes going like this. I'll have to insert something on this, but where we can see all 3 axes at an angle and maybe get a feeling for what that third dimension is. So that's what happens when you have 3 people. when was the last time we did an analysis of a large network with 3 points? When you start to get 1,000 points, you have 1,000 degrees of dimensionality, and you cannot represent that on a page. You cannot represent that with 3D goggles on, because that only gets you 3. That fourth gets hard. That once you get beyond the fourth, our brains are not very good at that. And so what we often engage in is some way of trying to take thousands of degrees or tens of degrees and smush them down into 3 or 2 degrees to be able to display them visually. And there are ways to do that try to distort that as little as possible, but it's impossible to depict it exactly. And as a result, particularly for high dimensional spaces of interactions, of complex interactions, that visualization is necessarily going to be limited. And so part of what we have to do is think about, when we depict something, how we pull out the most important stuff. And that dimensionality is a big piece of that as we get to more complicated sorts of stories. So this is just to say that in a second, I'm going to talk about how much kind of skill you need in dealing with the numbers, in kind of thinking through things numerically and particularly statistically to do data science. But I think that the most important piece of this is recognizing that even if you become masterful in the statistics themselves, that is rarely where the error is introduced. It's often in the story you tell on the front end and the interpretation on the back end, that you can have something that is true statistically without having something that is useful in terms of a model or theoretical fit. And I think that is more common than errors in the stats. You can keep your statistics fairly simple, but as they become more complex, you can introduce errors into that process as well. You can make some mistakes about your assumptions about the data if you're not checking them carefully, and that sort of thing. But far more common are the errors of having perfectly acceptable statistical analysis from the bracketed basis of assuming that your data is correctly collected, that your sample is appropriate, making those assumptions, coming out and having the back end. It is that process where you have the answer, where you have you've run the stats, you have some kind of if you're trying to do inferential stats, you have some kind of an error bar. And then you try to interpret whether that is useful to informing your theoretical concept. That's where the error tends to be, on the front end or the back end. So as we talk about quantification, I don't want to separate it cleanly, because it's never easily separable from that process of datafication and that process of narrative. And I also want to encourage you to think about what that means when you are trying to make sense. When as you're collecting, you're usually thinking about it from an analytical perspective. What is the model I'm collecting into? How am I going to show the relationship between these variables? You need to think about that from the outset. Like, if I'm collecting something into variables, I can't just be saying I'm going to collect these variables because they're the ones that I can see or the ones that I can get at. You need to think about whether they are appropriate to the kind of analysis you're getting and the story that you hope to tell. Some of this is kind of wishful thinking, is a large part of what we do, right? Will I be able to tell the story that I think I can tell? And will I have the self-discipline when I recognize that story is either too partial or incorrect to backtrack and either collect new data or do a new kind of analysis from the data that I have collected? And that is an essential part of what we all do when we try to come up with answers about the way the world works.